Hello. So far we have looked at planar 2D problems. Let us now turn our attention to another class of 2D problems called axisymmetric or RZ type of problems. In this particular example, notice that we have just two components or two parts or two bodies in our geometry. One, which I'm highlighting, is the coil. It's just a cylindrical coil, and then there is a top cylindrical plate which is made of steel. Now if you really think about this geometry, we call these type of geometry as axis symmetric. And why do we say that? We say that because, let me just turn on some surfaces. We say that because I could actually, if you just think about these two surfaces and you can revolve them around, say, this line, which is the axis of symmetry, if you revolve them 360 degrees, then you would actually end up with these two bodies. So when you have a geometry where you can revolve a group of surfaces and it forms a perfectly axisymmetric geometry, then we can do a 2D simulation to accurately depict the 3D geometry and get quantities like the magnetic flux, the forces, and so on. So let us see how we can use this axisymmetric concept to actually do a simulation on a coil which carries some current, and because the coil carries some current, it acts like an electromagnet, and because there is an iron cylinder at a particular distance, there's going to be a force acting on the iron cylinder, and this particular force is going to attract the cylinder towards the coil. So let us use the 2D simulation to compute the forces acting on the cylindrical surface due to the current in the coil. Now to do a 2D simulation, I can just go ahead, hide these solid bodies so that I'm just left with a surface that represents the coil, another surface that represents the cylindrical steel that is at a particular distance from the top of the coil. We also need a surface to represent the air geometry that surrounds this. And this was created here. So in the next video, I'll show you how to create these surfaces from scratch in SolidWorks. In this video, let's assume that these surfaces are there for you, and we will go to the simulation part of it. Now before we start the simulation, this would become familiar to you now, that we need to represent what is called as a coordinate system for our 2D simulation. In this particular coordinate system, these are classes of problems that are called RZ problems or axisymmetric problems. So we need to have the z-axis lined up with the axis of revolution, and also we need to have the x-axis, which refers to the radius or the radial component. Okay. Now this is the radial component. As you go from the axis, you go out of it, it's radial, and then the z represents the axis. Now we will have to do a simulation in EMWorks 2D. Now to do a simulation, we can go to EMWorks 2D Manager, and then as before we can create what is called as a study. We're going to take magnetostatic study, and in the 2D geometry tab we will select axisymmetric RZ type of problems. Remember, so far we have been doing XY planar type of problems. Now we will focus on RZ type of problems. You can select the coordinate system and then say OK to create the study. Once the study is created, we go over the steps in the order from top to bottom. Next is to apply materials to the various components. Now this first surface that I selected here, that belongs to copper. So from our favorite material we select copper, and I strongly encourage you to keep these favorite materials because it's really helpful to select them in subsequent studies. The next surface belongs to steel, again from my favorite material. I select steel 1010. And the last surface is the air geometry, again from the favorite material I can select air. Now once the materials are applied, I can just close this folder. Now the load restraint, if you remember, we did them in the XY planar as well. We have to denote the extremities of the problem, and that is done by selecting the edges that form the boundary of the problem, and not the symmetric edge. It's just the three other edge that forms the boundary of the problem. And then when you say OK, this denotes the program that these are the boundaries of the problem where the flux is negligible or it goes to 0. The next step is to define a coil. Now to define a coil, you right click and select solid coil and surface. You can select the surface that represents the coil, and here is where you would put the amp turns. So we can say 2250 amp turns, and we select OK to define the coil. Last but not the least, we have to request the program to compute the force acting on the top cylindrical plate. So again, you just select the surface that represents the top cylindrical face to compute the force and say OK. With this, we have completed the definition of the problem. We'll come to the meshing step. In the meshing step, I can right click, create mesh. What I would like to do is I would like to just have a much smaller element growth size and say OK, and automatically EMWorks will create an optimal mesh. And as you see here, it automatically puts quite a lot of elements in and around the steel and also away from the coil. So that's good enough. And with this, we can go ahead and run the simulation. You can right click on study 1 and select run. EMWorks 2D solver will run the simulation, and once the simulation is complete, we are now ready to take a look at the results. Now let's start with the magnetic flux density. So if I open the magnetic flux density folder and double click on the magnetic flux density plot, I can now see the magnetic flux density distribution in the model. I can also see it as a vector plot. I right click on magnetic flux density, I select vector plot and say no clipping, and here I have a vector plot of the magnetic flux density. It's probably useful to go ahead and reduce the size of the vectors. So now it's very clear. You can see the flux vectors towards the center of the cylindrical coil. You have more flux, and then it goes through and turns through the cylindrical steel and then completes the loop. So this is really the magnetic flux density vectors that one can see. You can even have them as just one single color so that it's very clear how the flux vectors are. Or you can match the color to the color chart and say OK. Last but not the least, my favorite is really to understand the flux lines as contour lines. So right click on the vector potential and then select the contour line format, and now this gives you the magnetic flux lines as contour lines, and this is very powerful. It kind of tells you where the high flux areas are in the model and how the flux lines are distributed in this particular axisymmetric surface.